Well, good morning. Hey, it's Monday, 4/20/20. I guess today we got 2020. Time to do a little bit of physics. All right, so here's what I want to accomplish today. I want to do a little bit more practice with you on some conservation of energy calculations. And then we're going to get into power. I want you to be able to define the word power as it applies to physics problems and do some calculations with it. And we're also going to get into the concept of efficiency. So again, I want you to be able to define efficiency and do calculations with efficiency. So for starters, let's just try to do another problem of conservation of energy. Okay? So here we got Wile E. Coyote. And he bought himself an Acme Giant slingshot. He places himself in a slingshot and he stretches it back 3.75 meters. And he waits for the Roadrunner. Now, if the slingshot launches Wiley at 34.0 meters per second, what was the spring constant of the slingshot? And I said, oh, by the way, Wiley has a mass of 18.0 kilograms. Okay? So what I'd like you to do right here, right now, is pause the video, see what you can do to work that up. Go. Well, my hope is that you just took a few minutes and you paused the video and you've worked out some things and maybe you've got an answer or maybe you're stuck on it, but I'll go through and work it through right now. Now, we're trying to do this in terms of conservation of energy. So if we think about it, we're stretching this slingshot back. That sounds to me like elastic potential energy. And when Wiley gets launched, he's got a velocity that seems to me to be referring to something with kinetic energy. And what we're going to do for this problem is we're going to imagine that all of the energy gets converted from one form to another. So we set these two equal to each other. Okay? Now, the formula for elastic potential is 1/2 K delta D squared equals 1/2 mv squared. I'm looking for K. I can simplify this a little bit because I've got a 1/2 on both sides, so I just multiply both sides by 2 and that's both gone. I think what I want to do next is let's get K by itself, so let's divide by delta D squared. Delta D squared. So now on this side I have K equals mv squared over delta D squared. And I'm ready to plug everything in. So the mass, Wiley has a mass of 18.0 kilograms. His velocity is 34.0 meters per second. That's squared, so I'm going to put it in here twice. Okay, and we're dividing by that distance. Now that delta D is the stretch, because that came from our elastic potential energy, so that's the stretch of our system, 3.75 meters. And what did I just do there? That I'm going to put in also twice because it was squared. Okay? So now I go back and I look at my labels and they're going to look a little bit strange, but let's work this out. It looks like meters all cross off, and I've got kilograms per second squared. And you might not recognize that as unit for K. What we're familiar with is newtons per meter as K. I'm going to leave that go and we'll come back to it in just a second. Let me extend this page. Let's do the math. We've got 18 times 34 times 34 divided by 3.75, divide again by 3.75. Okay, I've got a spring constant, K equals, let's see, looks like we're allowed 3 sig figs, so this would be 1,480 kilograms per second squared. That certainly sounds like a really weird label. I'm going to extend this a little bit. All right, so what we've seen in the past is that I said K is usually expressed as newtons per meter. Well, let's break that down a little bit. A newton is a kilogram times a meter per second squared. And this newton is divided by a meter, so I got to divide by a meter over here. And would you look at that? The meters cross off, and it turns out that a kilogram per second squared is the exact same label as a newton per meter. So what we just figured out was okay. Same label. Looks weird, but it's all right. So if you really wanted to, you could express this. You could now say that this is 1,480 newtons per meter. They are the same thing. All right. So there's a little refresher in your memory, hopefully, of some of the stuff that we were doing last week. All right, on for something new. Power. Yeah, we hear about power. A vast majority of athletic competition is all about power. It's not just about being strong. You know, when it's been a little while now, but you know, when I used to go in the weight room, boy, I loved to go to the bench press, and I could put a bunch of weight on the bench press, and I could make that go. And the thing is, in athletic competition, there's really nowhere that you ever have a situation where being able to move a heavy weight slowly is a great skill. What we want to be able to do in athletic competition is move things quickly. We want to be powerful. So power is the rate of using energy, or since energy and work are really just two different forms of the same concept, it's the rate of doing work. So as an equation, when we have a rate, that means we look at how long it takes you to do it. We look at a time. So power is energy divided by that time interval it's used, or power is work divided by the time interval in which it happens. Just take a look at units. So if power is energy over time, and energy is measured in joules, and time is measured in seconds, power is measured in joules per second. Well, we give that a new name. We call that a watt, capital W. A watt is a joule per second. Now, if we were to break this all down, and we know that a joule is a newton meter, and a newton is a kilogram times a meter per second squared, we would figure out that a watt is a kilogram times meter squared per second cubed. Maybe you can see why light bulbs usually are labeled in watts rather than kilograms times meter squared per seconds cubed. You will also hear sometimes about a horsepower. Well, a horsepower has been standardized as 746 watts. Originally, it was based on like the rate at which a horse could do work over a day. Certainly, a horse can generate more power than that for short periods of time, but it was averaged out over a day. It turns out that many of you, in short periods of time, can generate more than a horsepower. I used to do a lab here, and I would challenge students for anybody to beat me on generating horsepower. And in this particular challenge, riding up a little flight of steps, students couldn't do it. I don't make that challenge anymore because I've put on a few years and a few pounds, and now some of you might be able to do that. I've never hit 2 horsepower in any years that I tried it, but I quite often was up around 1.9 horsepower. But we're talking about an effort of 2.5 seconds. So let's do a power calculation. We've got an 85.0 kilogram football player, runs up 3 floors of stairs, a total height of 10.5 meters in 9.64 seconds. What power did he generate? Well, power is energy over time or work over time. I'm going to use work here. And let's think about what work he does. Well, work is force times distance. So power is force times distance over time. Okay? What force? We know the time, 9.64 seconds. We know the distance. He goes up 10.5 meters. What force? Now, 85 kilograms is not a force. And if you're still making that mistake, you've got to get past that one. Kilogram is a unit of mass. But if I got to lift my mass up the steps, think about it. If I put my foot on a step and I want to lift myself up that step, I've got to exert a force at least equal to my weight. At least equal to my weight. I can find the weight. The weight is m times g. So m is my mass, 85.0 kilograms, times g is 9.80 meters per second squared, and I get a mass in this, or I'm sorry, we've got a mass, I get a force or a weight of 85 times 9.8, 833 newtons. Okay, now I can go back to this and say, all right, there's the force. If I don't apply at least 883 newtons, that guy's going to stay at the bottom of the stairs. He needs at least that much. So 833 newtons times our distance of 10.5 meters divided by the time of 9.64 seconds. 833 times 10.5 divided by 9.64 equals 907. Should have left a little more space in here, but I'll just change my color. 907. A Newton meter is a joule. A joule per second is a watt. Our football player did more than a horsepower running up these steps. The challenge that we used to do was a much shorter flight of steps. Whether or not our football player could maintain that kind of speed up 3 floors, I'm not sure. But I think some of them certainly can. I feel quite confident that some can. So there's a basic power calculation. What's next? Let's take another look at that equation. If power equals work over time, and like I just did in the last problem, we know that work equals force times distance. Then we can write power as force times distance over time. But, hey, what is distance over time? That's a velocity. So what I could do is imagine taking that and replacing that with velocity. And so power could be written as force times velocity. There's an alternate power formula for you. Force times velocity. So power is work over time. Power is energy over time. Or power is force times velocity. All those are ways of finding power. So we got another example. A crane lifts 3,450 kilograms of material at a rate of 1.20 meters per second. What is the power of the crane during this lift? Okay, power equals work over time, right? But what were we given? We were given a mass, and we were given a velocity. So when you see that velocity in there, let's think about our alternate. Power is also equal to force times velocity. I have a velocity, and when I have a mass, I can calculate the force required to lift that mass, and that's called the weight. So I'm going to go off on the side again, say the weight is m times g, which is 3,450 kilograms times 9.80 meters per second squared. So, big number, 33,800 newtons. Okay? Yeah. We got almost 3.5 tons of material here. Now I can come up here and say, all right, I'm going to take all that weight, 33,800 newtons, and we're going to move it at 1.20 meters per second. Hey, look at these labels. A newton times a meter per second. Well, newton times a meter is a joule, and a joule per second is a watt. $33,000. I still have the 800. This actually came out to 33,810. I still have it in my calculator. That's all right. Times 1.20 equals, and now this final answer I round off to 3 sig figs. So we've got 40,600 watts. And you see that, gee, watts are pretty small. You know, a light bulb, you know, an old-fashioned incandescent light bulb, quite a common size, was a 100-watt light bulb. If one light bulb's using 100 joules per second, what do you think this crane is using? Wow. So, quite commonly, we might just write this as 40.6 kilowatts. Okay, going between kilo and some base unit should be a pretty basic conversion for you. All right. What's next? All right, so energy cannot be destroyed, but some energy forms are much more useful to us than others. And so we get this concept of efficiency. Efficiency is a measure of the portion of our energy that's actually accomplishing what we want to accomplish. And we express it as a percent. So efficiency is the ratio of the energy output over the energy input times 100. Likewise, instead of energy, I could have used the terms work in here. Work output over work input times 100 turns into a percent. So of the worker energy that we're putting into a system, what actually accomplishes we want. And now you can think about where would the extra, the leftover energy go? Well, it goes into noise, it goes into heat. You know, when we're moving something, if I walk through the air of this room, yes, I'm trying to move myself, but the reality is I also move a bunch of air molecules out of the way. Well, some of my energy went into moving those air molecules. Let's do a calculation. So we got a force of 225 newtons is used to move a crate up a 14.80 meter long ramp. The result is that the 248 kilogram crate now rests on the bed of a truck, 1.2 meters off the ground. What's the efficiency of the ramp? I think this one's worth a little sketch. So let's say here's the back of our truck, and we've got a big long ramp. We're going to take this crate, we're going to move it along the ramp, which is 14.80 meters long. But the result is our crate ends up getting lifted 1.20 meters. Okay? In the end, the crate's going to be sitting on our truck. It was a 248 kilogram crate. All right, so let's think about what did we accomplish if efficiency is the work output over the work input times 100. Well, work output, we can think in terms of gravitational potential energy. I lifted this object that far. That's the result. It was on the ground, now it's on the truck. Okay? So that could be our energy output. And that would be MGH, right? Potential energy. Work input, well, I applied a force of 225 newtons over that distance right there. So that actually fits my work calculation where, work is force times distance. So I take that whole ratio times 100. See, this is one where we really have to reason things out. We say, what are we accomplishing? What did we do? What we accomplished was we lifted this object. We increased its gravitational potential energy. What did we do? I did some work. But some of my work went to overcoming friction. It didn't just increase the energy of the object. So my efficiency is always going to be less than 100%. All right, I'm going to take that efficiency that we just reasoned out, and MGH. We got a mass of 248 kilograms. We're on the Earth, so G is 9.80 meters per second squared. The height was 1.2 meters. Okay? Now, on the bottom, the force I applied was 225 newtons. So I just put that into any open space on the bottom. The distance we applied that force was 14.80 meters. Okay? So let's take a look at labels here. Meters are going to cross off right there. This is a kilogram times, look at that. Right here we've got a kilogram times a meter per second squared. That's a Newton, right? And then we have a Newton on the bottom, so all of that crosses out, which makes sense, because the efficiency is just a percent. All the other labels are going to cross off. We do have to put on here times 100 yet. Okay, and I'm going to go to my calculator. 248 divided by 225 times 9.8 times 1.2 divided by 14.8 times 100. And extend my page a little bit. We just found out that our efficiency was, to 3 sig figs, 87.6%. So of the energy I used to move this crate, 86.7% went into lifting the crate. Honestly, in a lot of situations, that's probably not too bad. we can maybe make it better. It doesn't say we could put rollers under the crate and this maybe gets even better efficient. Okay. And yeah, that's as far as I was planning on going here today. This should hopefully give you enough information that you can finish off your problem set for the chapter. I am still working on how I can have you do some sort of lab activity at home. Struggling with that concept a little bit. If anybody's got ideas, let me know. As always, if you have questions, let me know. I can't help you out if I don't know what the problem is. Right? Have a great day. Stay safe.